All right, so we're going to just finish up going over the rest of the materials from the chromatography chapters. So the last thing I did this morning was talk to you about the plate height calculations. And the next thing was looking at resolution. And we said resolution was the effective separation. And I talked about this in the video. The key thing I just want you to realize that resolution, there's three factors that influence resolution. Efficiency, so you can make the peak sharper. So instead of having a big broad peak that's like this, if you figure out how to make your system so you had a much sharper peak, you could separate peaks easier. All right, so that's efficiency. Selectivity, the next term, is that if you could make your column retain one species over another so that they're further resolved from one another, that would give you a better separation. So on the selectivity term, instead of having two peaks that are next to each other, if you could have the two peaks that were resolved a further distance apart. So there's a greater difference in their retention times. That would give you a better separation. And the third thing is just retention itself. The longer things stay on the column, the longer the column, the more the ability to pull them apart. Okay, so if you, instead of using a 10 centimeter column, you use a 20, it should be a better separation. Instead of using a 20, if you use a 40, it should be better. Okay, so there's three factors that come into play. The one that's the easiest to give us our best separation, because it's a square root function, is resolution. We want our peaks just to be as sharp as possible. Probably the one we control most frequently is this guy. This is the easiest. Doesn't like we're going to write the highlighter. This is the easiest to control. So that's the parameter we typically try to go after, is try to adjust the selectivity to pull two things apart. And we'll talk a little bit about in GC and stuff. So instead of doing a clicker, we're just going to work with these all together as a group. All right. So on here, I've got a problem where I've got a component that elutes in 13.9 minutes. So this is its retention time, TR. And then it tells me that the shape of the peak width at the base is 18.8 seconds. And I want to know what's the number of theoretical plates. So in this case, here's my formula for the number of theoretical plates. And the one with the width at the base is this guy. So the plate number equals 16 times the retention time squared. So it's 13.9 minutes. But I need to be in a common unit because one's in minutes and the other one's in seconds. So I'm just going to convert it to seconds. Minutes cancel out. And I got to remember that that term is squared. Okay, it's squared here. And then just divide it by the peak width in seconds. So it's 18.8 seconds wide. And remember, it's squared too. So I put those two things together, and I can calculate the number of theoretical plates. And I got 31,500. Yeah, I rounded it 360. Okay.
Why did we do 16 t squared instead of 5.5?
Okay, because this is for the width at the base, width at base, which is what this one says. Okay, width at base. This one's the width at half height. At half height. So you just have to look and see what's given to you in the problem to know which form of it you use. All right? Okay, so this is a summary that's pretty much all the equations that we talked about. You've mastered this. You can do anything I'm going to ask you to do. So,
I didn't answer.
Say again?
I didn't answer.
Oh, we're not doing those.
Oh, we're not answering.
No,
No, I did them together for you. I worked at.
Don't worry about it.
You're good. Nobody else answered either. Yeah. So, but this is just a summary of all the equations in the chapter. Okay, so the last thing I want to talk about in chapter 23 is looking at why do the bands spread out. So I said plate height. I gave you a relationship to the plate count and told you the inversely related. There's an equation called the Van Dietner equation. And the Van Dietner equation relates to the different components that contribute to plate height. And it says that it's related to three terms. One is the multiple paths term. Two is longitudinal diffusion. And three is equal to the equilibration time required so that mass transfers kinetics are not feeding you. So if you think about these three terms and simply what they mean, the multiple paths means this. So you have a couple of particles of stationary phase, and your solutes are flowing down through here. And one weaves its way through there like that. And if the other one takes a more direct path, if they both started at exactly the same point, the one that went the shorter distance is ahead. Okay, so what we can do to minimize the band broadening from this is make all of our particles exactly the same size and exactly the same shape. So if we could, and this becomes an engineering problem, if we could manufacture every particle and they're exactly the same size sphere, and we pack them together as tightly as possible. So when we go to pack these things, we pack them with up to 50,000 psi, really high pressure. And we're trying to make sure there's no voids, trying to minimize that term. I mean, that's just an engineering problem. Now the diffusion term, there's not much you can do about diffusion because you can't stop molecular diffusion from occurring. What you can do is increase the viscosity of the solution. Okay, but the problem when you're pushing a liquid, so I've got a mobile phase I'm trying to push through here. If I increase the viscosity of the liquid, I can't push it through small particles. So, I mean, if I want to stop something from diffusing, I put it inside of a solid. Stop diffusion, but you can't flow it anymore. So that one's a hard one to balance. The last one is the equilibration time. So how long does something need to stay in a position until it gains enough free energy that it can do that phase transfer? Well, that's temperature dependent a little bit. But all three of these different terms, two of the terms are related to flow rate. The longitudinal diffusion is inversely related. So what that means, the slower I go, the more I get this thing to diffuse out slowly, the wider the peak's going to go. If I can make it go down the column quick, it doesn't get a chance to spread out. All right, so here the velocity works. The higher the velocity, the better off I'm at. But on this one, on the equilibration time, if I go too fast, the mass kinetics run off and they separate from one another. So this one, it's related directly. Here it's inversely related, so the two things are fighting against each other. So the result is you've got three different terms that add together. So in black, you've got the contribution that comes from the multiple paths term, A, and it doesn't matter how fast you're going, you're still going to have these things that are there. Then the B term is the longitudinal diffusion. It goes with the inverse. So the faster I'm going, so here is the flow rate in this one, the faster I'm going, the better. So I want this to be as small as possible. So low is good. All right, so the minimum is better for me. That's higher efficiencies. But the other term that comes in is the equilibration time factor. This one, the faster I'm going, the more the kinetics are not favored. All right, it'd be better if it were static, like happens in a septory funnel. So all three of those terms add together, and if I put all three of these pieces in there, the result is this type of a shape. And this is called a Van Dietner plot. And what it tells us is where this is the lowest, the minimum is the best flow rate. So I create this plot by simply, I do a couple of different flow rates and I just find out where it's the sharpest peak's at. All right, so it's not that hard to do in the real world. It takes an hour or two of your lab time, but it'll tell you where your peak's the sharpest at. All right, so here was a question I picked out of, this was year before last exam, the last time I did chromatography. It says the Van Dukener equation describes the plate height in the terms A, B, and C. Compared to the linear velocity, and want to know which one of the following is not true associated with it. In A, it says the value of A is column specific and dependent on the linear flow. Well, if I look at the A term, there's no flow term associated with it, so it's not A. B says B takes into account the longitudinal diffusion of the analyte in the mobile phase. Okay, I'm looking for the one that's not true. I've already answered it. That's the one that's not true because it's not linear flow dependent, right? B does. B is a, so if I look at this one, B is a true statement. That's what B accounts for, is the longitudinal diffusion. C takes into account the equilibration time between the two phases. That's a true statement. And the mobile UX represents the flow rate of the mobile phase. D is true as well. So here, looking for the one that is not true is choice A. All right, that was one of the multiple choice questions that we had. So here were a couple more questions from that same test, just to give you a few more. So number 9 says calculate the resolution for two adjacent peaks. Tells me one elutes at 1770 seconds, and the second one elutes at 1800 seconds. And it gives me the peak widths of peak 1 and peak 2 of 51 and 57 seconds. So I'm looking for resolution. So I'm going to use the resolution equation. So what I've got is peak widths at the base now. So instead of using this formula that we used in the calculation this morning, now we've got to go back and use this one. Okay, so our resolution is equal to the difference in the retention times. That's the easy part. So 1800 less 1770 seconds. That's just going to be 30 on top. And then on the width, I just need one half, or the average peak width. So I'm just going to take the two things and average them together. So 51 plus 57 seconds. So if I average those together, 854. So I've got 30 divided by 54. If I did my math right.
So this answer is always above what's below 1?
No, it could be either.
Okay.
Selectivity is always above 1. The alpha term,
Okay.
But resolution can be 0. If two things are co-evolving, resolution 0.
It can be, but it can be lower.
Can't be negative.
What years is it there?
15, I think, because last year I didn't get into any chromatography. All right, number 10 says calculate the theoretical plates for a peak that had a retention time of 1295 and a width at half height of 9.3 in a 15-meter column. So you may see the same type of problem, and I may ask for the plate height. So instead of looking for the number of plates, where this one's asking for plate number, you get plate height. If it were that case, we'll do it both ways, but here we're going to do what it asked for first. Okay, so we've got, need to use the equation for plate number, and it gives me the peak width at half height. So that means I'm going to use this form of it. So it's just a matter of plugging in. So n equals to 5.55 times. My retention time is 1295. And both are in seconds, so everything was good there. So seconds divided by 9.3 seconds. And I got to square both of those terms. And that's a pretty sharp peak.
You ever actually had to use this stuff?
Me? I got a PhD in this stuff.
That's a
I've done hundreds of thousands of these calculations. Yeah.
What is T? It's a retention.
It's retention time? Yeah.
Seriously.
Okay, so
Yeah. All right.
all right, 1.1 times 10 to the 5th plates. So that's the number of plates. And now I ask you, if I were to ask you what is the plate height, so instead of asking for the number of plates, if I'd ask you what is the plate height for this system, height is equal to the length divided by the number of plates. The length of the column is 15 meters divided by this huge number of plates. So it'd be 1.4 times 10 to the minus 4th meters, or if I wanted to put it in a metric equivalent, 0.14 millimeters. Okay. All right. So just the type of calculations that we'll need to look at. All right. Switching to the next chapter. So most of this stuff is just the notes. So you can watch the videos, and we're just gonna we're not using Flickr, so we're just gonna get rid of that. So it's not in the way. So with GC, the big thing about GC is now you've got a gas phase that's your carrier phase. And the critical thing is that for something to be able to move along the column, it's got to move in the gas phase. So it's got to be volatile. All right, so this doesn't work for ionic compounds. It doesn't work for proteins. Anything that you would heat up and it would decompose instead of going into a gas phase, not for GC. This works for the volatile stuff. All right. So the column has to be hot enough to give you enough vapor pressure so that the analytes can elute. So what does that mean? Well, the water that I just spilled on the tabletop here, when I come back in the morning, it'll all be evaporated. And the room's never going to reach the boiling point of water. Why? Because there's always a vapor pressure. The solvent's constantly going into the vapor. And the hotter it is, the higher that vapor pressure becomes, and the quicker and quicker it's going to escape from the surface into the gas phase. So that's what we do with the GC column, is we start to get up closer to the boiling point to allow it to escape into the gas phase easier. Typically, you're going to run your column around 50 degrees less the boiling point. All right, that's a typical time that you might run. So the columns, almost all the columns today are these little capillaries, and the scale here is something you have to kind of wrap your mind around. The internal diameter of these are anywhere from 100 microns, tenth of a millimeter, twice the thickness of a human hair, up to the largest ones are about half a millimeter in size, and that's called a megabole. Most commonly, we use the 100 to 250. And then on the inside wall of these things, we put our stationary phase. So you got the gas that's flowing down inside of here, and then the stationary phase. And then we can put the stationary phase just as a viscous film on the surface, or if we need more surface area, we can put particles on the side of the walls. I mean, it's just an engineering issue that's been conquered. If we need even more stationary phase, we can fill the whole capillary tube up with little tiny particles. These are things that we engineer very specifically. Now, I told you that we had a column that was 150 meters long. It's not stretched out in a straight line. It's rolled up into a spool. Okay, and this whole thing fits inside an oven that we very, very precisely control the temperature on. So you might review the definitions, Walcott versus Scott, understand the difference in those. What are the common sizes I just mentioned in terms of the columns. And when we talk about how things are going to elute off of a column in GC, the thing that's most volatile is the thing that's going to come off the column first. So the compounds with the lowest boiling points elute first. Okay? So if I looked at this example, here's a mixture of solvents, and then there's some straight chain alcohols. There's one butanol, one pentanol, one hexanol. And there's a branched hydrocarbon in here. The branched hydrocarbons, if you remember, are organic, have lower boiling points. Okay, so it comes off first, and then the compound with the next boiling point, and then the next boiling point, and the next boiling point. And this goes back to one of the problems that I talked about in the last chapter. See how this peak's fairly sharp? And on this guy, as it starts to stick out, peak's getting broader and broader and broader. All right, and if I went to the C7 instead of C6, this is C6, C5, C4, C7 is like out here somewhere. Okay, you're talking about several hours for it to come off the column. And you'll never get C8 off the column under these conditions. So what we do to get the larger ones off is I'd increase the column temperature of the oven. So if this was ran at 50 degrees, whatever the temperature this one was, I would increase it to maybe 75 Celsius. And then I would get these guys that were down here to come off the column. All right, so let's see, raising the column temperature increases retention time. That'd be a false statement. Whenever the oven temperature goes up, everything's going to come off faster. Okay, because you're going towards volatility.
You said Dr. Piva has one of these?
Well, we have 3 of the instruments downstairs. She has one particular column she uses for fatty acid analysis.
Oh, it's not a...
It is a Gastromat. We have 3, and take instrumental, that's the thing it's one of the topics we learned. We have 3 GCs for the department.
So you can't use like that for biochemistry applications.
Sure. Yeah, all the time. I mean, most of the stuff that I do in my work is with microbiologists, biochemists, and I solve their biochemical problems. So we do work with amino acids, carbohydrates, small molecules, metabolites, thousands of different types of seeds. So, right. So the stationary phases, the rule that we use, and I went over this as note, is that the like interacts with like. This is where you got to remember those intermolecular forces back in Gen Chem 2. What makes a solvent stick together so it has a high boiling point? So remember your intermolecular forces. What's the strongest of the intermolecular forces? Ionic strongest. What's second strongest? Say again? This is intermolecular. That's intra. The super dipole hydrogen bond. Okay, and then it's dipole interactions, and then you go induced dipole interactions, and then finally you got van der Waals forces down the end. Okay, so you've got this order of things of how they interact with one another as a solvent and would stick together. The same type of thing happens with the chromatography. You want to choose a stationary phase that has the properties that matches your analyte. If you want it to stick to the column while everything else runs away on down the column, you've matched the properties. So if you have things with aromatic rings that are fluorinated, you put a stationary phase that's aromatic rings. There are literally thousands of different types of stationary phases that they make. Almost all of them are combinations of silicon ethers. So they have this backbone of silicon dioxide. And they substitute whatever R groups in that they want to get the separation that you need. So things that are nonpolar, they'll put methyl groups on there, and to increase the polarity, they'll put phenyl. Phenyl is not polar itself, but it's polarizable. So if something that has a dipole comes into that, you can get charge separation within the aromatic ring. All right. If you want something that's more polar, you put a permanent dipole, like a cyano-propyl group in there. If you want to be more polar, something that's strongly polar, so hopefully none of you get to the point where you get to go to the hospital and they draw your blood, okay, from a DUI. So if you're suspected of a DUI and it's involved in an accident and anybody's hurt, you go to the hospital and they'll ask you voluntarily to give blood. And if you refuse to give blood, they tie you down the table and take your blood anyway. That's the law of Oklahoma. That's the way it works. Then they'll take that blood sample. Yep. They'll take that blood sample and they send it to Oklahoma State Bureau of Investigation right across the street from University of Central Oklahoma in Edmond. And that's where the core lab is, central lab. They do a headspace analysis, so they'll take and throw a little bit of salt in that blood sample, shake it up, and that kind of forces some of the ethanol out of the solution, and then they'll take and pull a vacuum on that bottle and pull some of the gas off of it, shoot it in the instrument. And ethanol is so volatile, okay? Same way that you smell ethanol coming off somebody's breath when they're hammered. It doesn't stick to columns very well. So it's a polar compound. You need to have a highly polar column to have it stick to. So they use a column called Carbowax. We'll use the same one next semester. So here's an example of some things that are gases at room temperature and how you could use a polar column to analyze those. Like acetaldehyde, something that's in your breath all the time. Methanol, here's ethanol. That would be the component that's we're seeing here. And just a list of different compounds that, I think these are actually breath samples. Okay, so these are different things that you think of methanol as being a poison, your body actually metabolizes, makes a small amount. All right, so these are all different types of things that you would find. Okay, so here we identify things based on the retention time. So whatever this time is, so time X is equal to whatever it is, that's where I expect to find ethyl caprolate every time. So if there's more of it, the peak gets bigger. If there's less of it, the peak gets smaller. I do a comparison of how big the peak is, the area underneath the peak versus the concentration, and that becomes my calibration curve. So I plot peak area versus concentration of standards, and there's a linear relationship. And I can use that to find out how much of ethanol is in a sample. All right? And this is the same type of thing. If you're convicted in the United States anywhere, it requires a GC blood alcohol analysis. The breathalyzers are not legal in any court system because there are too many false positives. Okay, too many things give you a false signal for this. All right, here's an example of the same group of compounds by just changing the stationary phase up a little bit. So on the column on the right, or on the left, your left, sorry, here's components 1 through 10 eluting off the column. And this is a nonpolar, so this is a dimethyl siloxane column. And then they took the same thing and ran it on the PG column, which is a strongly polar. And now not only does the retention times change a huge amount, but even the retention order. So compound 1 is now to sit in the middle of it. Compound 2 is up here. Compound 3 comes all the way out here. And why? Because it's a very polar compound, and it interacts with that stationary phase a lot. So this is the example of changing selectivity. I'm changing the selectivity to get a different separation. And that's one of the things that, that's the reason, I mean, the company that I worked for in St. Louis, we had all these different divisions. Monsanto, we had a pharmaceutical division, ag products. We had 12 different operating units, performance products, polymers. We made the hydraulic fluid that went up in the space shuttle. I mean, we did all types of synthetic materials, inorganics, small chemicals. My job daily was somebody give me something they couldn't separate, and they wanted to know what was in that mixture. And I would try to figure out how could I use GC, HPLC, or some other chromatographic technique to resolve a mixture. Tell them what are the percentage of the different components that are there. So day in, day out. All right, now one of the problems that we run into is that if I have a group of samples that vary a lot in terms of their characteristics, they don't come off the column easy. So this is a mixture of straight chain alkanes, and going from something like octane, so 8 carbons in a row, it's got a boiling point of 126 up to C14. Okay, so tetradecane is 254. Okay, so that's a difference of about 130 degrees boiling points. And what I see is that all these components that elute up front come off pretty good. There's a couple here that are actually almost co-eluting, but as soon as I get past C15, I'm an hour and a half into the run. I can't get things off. So what we do in GC if there's no one temperature that can resolve the complete mixture, we do temperature programming. So we've got this thing inside of an oven and air spinning around it quickly. We control the temperature of that oven so that we ramp the temperature up as a function of time. So we inject our sample, and here we're starting at 50 degrees Celsius. So we're starting the oven at 50 degrees Celsius, and during the course of the run, we're ramping the oven temperature up to 250 at the end. So one thing I get as an advantage is now I've got all these components well resolved. Okay? The other thing, tell me something about peak shape you see.
It's like an upside down purple. It's pretty sharp.
Okay, pretty sharp is what I like. Look how this peak, how broad this one is versus to how sharp these guys are down here. The temperature programming refocuses them. Okay, so that allows me to stack. If I had lots of more compounds in here to separate out, I could put umpteen more compounds in here and still resolve them. So this is where that efficiency, the sharper the peaks, the better off I'm at. So that's how we do it in GC. The sample is most commonly injected as a liquid, but you can get away with doing a gas. You want to use a very volatile solvent because you want it to evaporate off before any of your sample does. So you're limited on your solvents you can use. So things like ether, that's ideal. Hexane, methylene chloride. Acetone's about as high as the boiling point as you want to use. Maybe methanol. But you wouldn't want to use anything higher than that. We typically inject 1 microliter. That's a pretty standard size. Now it's hard to reproduce 1 microliter, so you've got a really small syringe. So it's a little glass-filled syringe. And the tire syringe may hold 5 or 10 microliters. It's got a sharp needle on it, so you're going to have to stick it through a rubber septum to get it inside of the system that's under pressure and temperature. So there's a thing here called a septum. I'll show you in just a second that you're going to have to penetrate with the needle. And because we're trying to make this reproducible, what we do is we typically pull a plug of air first. Right? Then we pull a plug of solvent, like a microliter, another plug of air, and then a plug of sample, and then a plug of air. And the reason we do that is because the solvent's going to flush anything that's in the syringe out when we mash it in. And the reason that we've got a plug of air in here is that as we start to put this thing inside of this, injected inside of here, it's instantly going to hit high heat. So this region is typically cooking. So you're at 250 degrees or hotter. And it's hot enough that it's instantly going to start boiling that solvent. So what you do is you have this void of solvent initially. So you shoot it in there. All right. Now that's if you're doing it manually. Today, we do it mainly with robots, and the robots makes life a lot quicker for us. So the injection port, I talked about in the videos how the injection port works. Most commonly, we do what's called a split injection. And with a split injection, even though I'm only putting a microliter in the instrument, only 1 part goes onto the column. And 99 parts go to waste. Because these columns are so small, they can't even hold a whole microliter. If you take a column that's 50 microns in ID, each meter long in length only holds 1 microliter of volume. So if you put a full microliter in there, you're filling up the column for a meter in length. That's not what we do. So problem is I really only want to inject about 10 nanoliters, and I can't do it. It's just too small. You're talking about the size of a cell at 10 nanoliters. So what we do is we inject a big sample, and we run into this splitter. This takes it into a gas phase. So here the sample's all converted into a gas. And then we have a set of just splitter control valves where it's easier for the gas to pass this way, and 99 parts of it go this way, and only 1 part goes under the column. It's called a split injection. All right? And then this thing that's in here is called a liner. It's there to, if you have salts or non-volatiles, it'll actually plate out in here and this is a disposable component that you have. Okay, so isothermal separation, I got three things that elute at 0.95, 1.5, and 8.4. What can I do to give you a better separation? So just mentally think about what this separation looks like. I've got time. 2, 4, 6, 8. It's 2, 6, 8. All right, so I've got two things that are coming off about a minute. And I got something else out here at 8.4. So what I'd like to do is I'd like to eliminate all this stuff. So I would want to start this at a temperature where these are allowed to separate out, and then I want to rapidly take the temperature up. So I do temperature programming. So I'd run a temperature profile that whatever these two separated out as soon as those two things are off the column, I'd very rapidly take the temperature up to a higher temperature to move this peak forward in the separation. If I did that, I probably could get it to separate in 2 minutes. All right, that comes with experience in playing with these things. All right, last chapter. So fewer slides on HPLC. So HPLC uses a liquid phase now, and we do two different types of HPLC, what we call standard HPLC. High performance liquid chromatography, high pressure liquid chromatography, depends on who you ask. It runs pressures up to about 3,000 PSI. The latest and greatest craze is ultra high performance liquid chromatography. It runs pressures up to 40,000 PSI. Now 40,000 PSI is crazy pressure. A 30-06 typically has a chamber pressure of around 32,000 PSI. 32,000. So this is running in excess of that. So that means if a fitting blows off, it's got enough pressure behind it that that fitting could blow off like a rifle bullet. So they really had to work with the design of this. The guy that came up with this technique was a guy named Jorgensen at University of North Carolina. I got to go to his lab once when I was in the industry. They were so afraid of this technology, they got a surplus tank turret and put down the basement of the lab and put the instrument inside of it, and they'd open the turret and you'd go down there and get everything set up, and then they close the turret and turn it on and ramp it up to pressure to see what it would take before it would blow. Thankfully, it's if the pressure is not confined, it dissipates as a gas very quickly, and it's not really like a grenade going off. It's not quite that bad, but today we conquered that technology, and it's easy to use, and it is the standard for separating things that are non-volatiles. So it uses a liquid mobile phase, and that's what causes the high pressures. That now you're forcing this liquid through these little tiny pores, and these particles that are micron size. And when you do the ultra high pressure, now you're sub-micron size. So you've got a series of pumps and detectors that allow you to see things. I took the slides that were in the notes and I cleaned it up just a little bit. Why do we do HPLC? Is because it's what we have to do for non-volatile species. GC works great for volatiles, but 70% of all the things in nature are non-volatiles. They're ionic compounds, they're salts, they're peptides, they're sugars, they're things that don't go into a GC. We have different modes that we can use. So absorption, partitioning, ion exchange, exclusion. These were the 5 modes that I talked about at the start of the chromatography chapter. And I went over the components that you find in an instrument. All right, here's one that's a test question somewhere. So this is a slide to figure out. Knowing how, if you change the mobile phase, you change the separation. Right? So if we change the solvent, we change how the stationary phase interacts with the solute. So in absorption chromatography, you use a polar stationary phase and a non-polar mobile phase. And it becomes a stronger solvent, so a stronger mobile phase with increased polarity. increase polarity. So I start off with something like hexane, and if it's not strong enough to move my compounds down the column, I add something like ethyl acetate to it. Make it a little bit more polar. And if that's not strong enough to it, I add a little bit of maybe 1% methanol. Something with a little bit of polarity to it. Now reverse phase is the opposite. Reverse phase switches the stationary phases around. It uses a nonpolar stationary phase, and it uses a hydroorganic solvent, but now you've switched your relationship around. So the stronger mobile phase with the lowest polarity solvent. So more organic, less water. Okay. Now the difference in the two things means the retention orders are going to reverse between the two compounds. Okay. So what I'm saying is that this is normal phase chromatography. This one's reverse phase. And I've got these three different components that elute off. So A, B, and C. So this is a low polarity mobile phase. It's a weak, low polarity. That's the weakest of the solvents for absorption chromatography. And they elute off in the order of C, D, A. And if I increase the polarity just a little bit, it becomes a stronger solvent. All right, increase with the stronger solvent. They now just compress and come off the column quicker, but the order doesn't change. All right, so if I look at this, if it's a polar stationary phase and like dissolves like, that means compound A is the most polar. It's going to be the thing that sticks to the column the most. All right, and C is going to be the least polar thing. So I can actually run things on the column and I can learn something about their polarities. All right, learn about physical properties. Now, if I run the same three compounds on the reverse phase chromatography, the retention orders completely reverse. Because now the thing that was the most polar is the thing that sticks to the column the least. So this was our most polar compound, A. Now it's the thing that likes the column the least, so it flies right off the column. Right? But the thing that was the most nonpolar interacts with the nonpolar stationary phase the most, and it sticks to the column. All right? So this is a high polarity solvent, so maybe this would be something like 95% water with 5% methanol. And then if I want to increase the strength of the solvent, what I do is reduce the percent water and increase the percentage of the organic. So maybe I'd go to a 60-40 or something like that. And what happens is they stand the same order, 1, 2, A, B, C. It's just now they're compressed to come off the column quicker. All right. We can change the composition of the mobile phase to have huge changes in retention, much more so than in GC. In the same way that you did with GC, you try to match your stationary phase to give you the retention that you want. Sometimes we can run with a single stationary phase, so we don't change the composition of the mobile phase. That's called isocratic. If we do change the composition of the mobile phase as a function of time, it's called a gradient run. Okay, so here was a test question from a couple of years back. It says a normal phase chromatography uses a blank stationary phase and a blank mobile phase. And it says the blank the mobile phase, the stronger the eluent becomes. So the answers that you can fill in with are polar and non-polar. All right, so what is the stationary phase in normal phase chromatography? Is it polar or non-polar? It's polar, and then it uses a non-polar stationary phase. All right, so to be a stronger solvent, do I want it to be more polar or more non-polar? More polar. I want it to match the stationary phase, so I want it to be like whatever the stationary phase is, and that's more competition. All right. So that was a test question from a few years ago. Okay, so here's another question. Was a multiple choice question. It says you're doing reverse phase chromatography. So remember, in reverse phase, it's a non-polar stationary phase. Non-polar stationary. All right. And I want to know, given these three compounds, how they're going to elute off the column. So all of these, if I look at the structures, they all have 12 carbons in them. They're all C12s. Okay. C is a straight chain N-alkane, so it's an N-alkane. And then I've got one that's a single alcohol, an N-alcohol. And then A is a diol. So which one's the most nonpolar? A, B, or C? C is the most nonpolar. So most nonpolar, that means it matches that of the stationary phase. It's going to be the last one off the column. And the thing that's the most polar is the one with both alcohols. Most polar, first off the column. So I would expect the retention order to be ABC in this guy. Yep. All right, so you'll have a question like that, more likely. All right, tell me something about retention. Here's just examples of different solvents and changing the composition of the solvent. So it's going from a solvent that's way too strong. So this is the B percentage is the percent organic. So percent organic. So this is 90%. Everything elutes in 5 minutes. Drop down to 60%. Now the things are starting to separate out, but it's taking 12 minutes. Go all the way down to 35%. To get everything off the column takes 125 minutes. Takes forever. That's huge resolution, but it's wasted time. All right, so that's not practical. These are all examples of isocratic separations. I'm not changing the solvent during the course of the run. It's staying whatever percentage that percentage is the entire run. So the way that we overcome this is we do gradients. So we change the resolution as a function of time. All right. So in this is the presentation in our textbook the authors used. And I'll tell you, if I were to have taken this to my boss in industry, he would have said, "You're crazy, because you got way too much space in here." The author's proud of the separation, and I'd tell you this is a waste of solvent. Okay? Because you don't need things, as soon as you get things resolved with a resolution of 2.5, that's all you need. Anything beyond that's a waste of time. So I would tell you on this one, yeah, it needs to be flat here to get these three compounds resolved. And then you need to move these things on down the column. I'd go a very, very steep gradient to here, and then probably a shallower gradient to get these last things off. But I guarantee you I could cut this down to, if not a 15-minute separation, 20 at the max. And they're doing it in 40. If you got a pump that's flowing a mill a minute, saving 20 minutes saves you that much solvent, 20 mils of solvent. And you think, well, I don't care, what's 20 mils? Well, over the course of the day, saving you the 20 mils in the run, saves you a couple of liters of solvent. Acetonitrile, the solvent they're using right here, acetonitrile is a common solvent that we use, and it used to be a waste product for the petroleum industry. And I could buy a 4-liter case, 4-liter bottles, 4-liter bottles of chromatographic grade acetonitrile for about $40. Now those same 4 bottles cost me $600. Okay, so now the less solvent I use, much, much, much better off I am. Okay. So one of the problems is coming up with the balance of how we get the best separation versus the best time. We can do that by making our particles smaller. So typically in LC, we're going to get particle sizes down to less than 5 microns. We want to make it as uniform as possible, and we want to try to minimize the distance for things to diffuse, so we try to make everything as compact as possible. That's the latest trends. So this just gives you an idea how much the Van Degenhler changes for different size particles. This is a 5 micron particle. You get these plates. If I just cut my particle by about a factor of 3, now two things happen. Number one, my plate height goes down, so my peaks get much, much sharper. So here's the separation with a 4. Here's the separation with a 1.7. Right? Now my time is a little over a minute, and my peaks are super, super sharp. Less solvent. Okay? Less money. That's where I want. The other advantage to this is these peaks get broader, they get shorter. Okay, so as they start to get wider, they get shorter. The concentration spreads out. So if I want to see something at higher sensitivity, low and lower concentrations, this is the big winner. So the higher sensitivity allows me to see lower and lower concentrations. That's another thing driving these small particle sizes. So this is the trend. We're not all instruments are there yet. I'll be glad when we get there, but we don't have one at this point. What's what?
I hope that's a relationship question. Less solvent, less money.
Yeah, you know. All right, so this last slide is if you ever got out in the real world and need to do HPLC, there's a lot of answers right there. It's your flow chart. But that's the challenge, and that's one of the things that you didn't realize in organic. But if Dr. Wiseman would have handed you a PLC plate without any solvent and said, resolve this, you could have spent days trying to figure out what the solvent combination that you need to resolve the spots you need the spot resolved. The difficulty comes in choosing the correct combination of mobile phase and stationary phase. That requires experience as much as anything, but just some general knowledge is down here. Okay? All right, that's all the notes I ever hope to get through this course, and we did a lot of material this semester. I'm fully aware of it. There's nothing more that I would want to give you. So what we'll do is test Wednesday. Friday, I'll give you your test back. We'll go over it quickly, and I'll talk about the things that'll be on the final exam. Steady. Old test outside my door.
Give us a, not a study guide, but something for the final.
I will give you a study guide for the final. So, I mean, we'll go over what's going to be on it
Okay.
in class, and type of material. Okay?
Fine.
We're not there. No, we're through now. So no more quiz.
I'll be gone for drill Friday, Saturday, and Sunday.
Okay.
Are you going to be able to record lectures?
Yeah. Yeah. We had never had